Thank you, and I'd like to thank the organizers for inviting me to this really nice workshop. So I will continue to talk about superconductivity and altermagnets, and I'm also going to talk about the diode effect, but from a slightly different state. I don't need to introduce altermagnets here. I was going to say I have one slide on, or a few, on how to set up the system that we study on when we add superconductivity to altermagnets, but then I hope to get rather quickly into the results, so I would like to go through at least 3 different results today. So first I want to show you this very easy to get finite momentum and field-induced superconductivity in an altermagnet, if you allow it to at least be superconducting or close to in a proximity-induced fashion. I'm also going to show you that it's possible to get a perfect superconducting diode effect where we have a supercurrent in one direction but none in the other direction. And that happens because of the finite momentum state. And then I like to highlight a little bit that one should be a little careful in thinking about superconductivity in altermagnets based on essentially the sublattice structure. One needs to think a little bit about that. And we also have some result on altermagnetism and superconductivity, well, altermagnets in strontium ruthenate, which is an intrinsic superconductor, but I don't think I have time to cover that today, but if anyone is interested, I'm more than happy to talk about that later. But before that, I should acknowledge the person who did all the hard work here, and it was done by Demala Chakraborty, who was a postdoc of mine, here up in the, sorry, I don't know where I am, here up in the corner. He moved recently to a faculty position back in India. The ab initio results was also done by primarily by Carmina Oteri at MagTop in Warsaw, together with a few collaborators in Italy. And of course, without funding, none of this would have happened, so we're very grateful for that. Okay, so we started thinking about, I didn't know much about altermagnets, but I worked primarily on superconductivity. So we started thinking about, okay, what would be interesting if there were superconductivity in an altermagnet? And we think, okay, so how would you get it? Well, it would either be intrinsic, and then there was this idea that maybe some of the pairing cuprate compounds were altermagnets, so that was interesting. As we saw, the strontium ruthenate is very close to being an altermagnet, at least if you distort the oxygen octahedral a little bit. Or as we heard this morning, you can get it by proximity effect. So we thought it was relevant to consider the combination of superconductivity and altermagnetism. And the way we were thinking about it was sort of coming from a very simplistic model. So if you start with a metal, you would then pair, see where I'm here. You would then pair from, if you at least consider spin singlet pairing, you pair K to minus K, and they have different spins, so spin up and spin down. And this would be obviously a zero momentum pairing. I'm just going to call this BCS pairing, even if I technically maybe have it as being D-way, but it's zero momentum pairing. But we also know, since a long time back, is if you have a ferromagnet, you can easily get a finite momentum pairing, and that simply comes from, if you insist on having spin singlet pairing, then these are not aligned, so you have K at up here, but that connects to the spin down, the minus K plus Q, and this Q then is the finite momentum, and is a finite central mass for the Cooper pair. So we were just asking, what happens in the altermagnet, but what happens in the ferromagnet is that if you increase the spin splitting, so in the ferromagnet it would essentially be the amount of spin splitting, or it could be an external magnetic field, you go from the BCS pairing to the finite momentum state, and then eventually you kill everything and you enter the normal state if the spin splitting is too big and you're insisting on spin singlet pairing. And this has of course been known since a very long time back, and since the 1960s, and often considered either as a full differential state where you modulate just the phase, or as a Larkin-Vishnikov state where you can modulate the amplitude. Also some combination of this in just a simple thought of as an FFLO state. So we were thinking, okay, so what happens in the altermagnets, because you have a little bit of both there. You have the nodes where the Fermi surfaces align up here, and you could imagine you should get BCS pairing, but you also have this antinodal region here where it sort of looks like, shouldn't I get finite momentum pairing? So we were simply wondering what will happen. So we set out to actually calculate this, allowing for a finite Q. And the phase diagram essentially looks like this. So this is what I will get to in a couple of slides, but let me first introduce how we actually got there. So it has a lot of different phases, well, have several different phases, and the valve varies both with altermagnet strength and magnetic field. So we set up a simple model to try to address this. So first we had just an altermagnet band structure. We've seen that earlier today here. So we had a D-wave spin split Fermi surfaces. We allowed for an external magnetic field, so we can further tune our structure. And then we have the superconducting pairing. And we saw this self-consistently within mean field theory, but we allow now for a finite Q. So that means we have order parameters that are, the Q is going to be sort of a fixed. For each Q, we calculate this solution self-consistently, and then we minimize the ground state energy. We get that as a function of Q, and we find the optimal Q that we're just going to call Q star. It has the lowest energy. And if Q star is 0, I have BCS pairing. And if I have Q star finite, I have a finite momentum state. So we take this, and obviously we need to do this in Will space, so we get the modulations allow for those as a function of Q. So first we turn off the magnetic field, and we just look at conventional S wave. So of course what we need to do here, we have to choose this V term here. So first we show V, so you just give us S wave pairing, we do that by just having a constant V, which will just be an on-site attraction. And then they turn out to not be very exciting for what we were looking for. We get BCS pairing, and at some point, if you crank up the spin splitting, this is TAM in this case, it dies out and we get a normal state. And we can understand that by looking at the pair density in the Brillouin zone. So here we plot the pair density, and you see in this nodal regions here, it's highest, and this is actually sufficient condensation energy to get BCS pairs at these nodes. So that means that I do this, and then there's no options to get this FF state here. Towards the end of the talk, I'm actually going to come back to what I don't think this S wave is very likely to happen out of altermagnet. And here it's a little hidden. We have essentially have to crank up V to get this BCS state to survive for some extension of TAM. Okay, so then we say, okay, that was a little boring. Is there any other possibility? And we were a little intrigued by this pairing cuprate compound, so we looked at D-wave state too. So then we have this V, the attraction, V here. We did just a nearest neighbor attraction on this. So then you get the D-wave channel, you also get the S-wave channel. It turns out the S-wave is not there, so we just get a D-wave pairing. And then we do get some more interesting things happening. So first we get the BCS state, but then there is a finite redeemer. We have finite momentum pairing in the system. Before, of course, we have so much spin splitting that we can't have any superconducting state in the system. So now we turn on, also it can tune an external magnetic field, and that's when we get this phase diagram as I showed you before. So this is the altermagnet strength here on the x-axis and the magnetic field on the y-axis. And I looked at it first and I thought it looked a little bit like a Yoda ear, so we call it the Yoda phase diagram. I don't know what your association are, but well, maybe that's why we call it a little green too. Yes. Yes. Yeah?
You were not here, but in my talk on Tuesday, I mentioned my work with my student, Soto Garrido, back in 2014. We looked at this problem in the continuum as a Pomeranchuk picture, and we looked at the interplay of FF and LO, and LO always wins. At the quadratic level, near the onset, if you do a Gorkov type calculation, they are degenerate. But the quartic terms favor the Larkin-Ovchinnikov state because you have two complex order parameters, and therefore you gain in condensation energy. So the FF in that out in that sense. Of course, if you put a magnetic field, I don't know. Maybe it's a different question. But in principle, the state that you get is a pair density wave, as I like to call it.
Yeah, yeah. No, it's a good comment.
Which is what we were after at the time.
Yeah,
that was the issue.
So we did only look at the FF modulation because we were looking at will the modulated superconducting state be more stable than the uniform superconducting state, and that we show by because FF is better than the BCS Then we did not look at the LO state, and primarily was because we thought it was going to be coexisting with a charge density wave, and we didn't want to disentangle that in our self-consistent calculation. So we settled on saying we call it FF, but if you want to say it's a broken translation symmetry state, I'm all for that. Yeah. So we didn't look at that, but I believe that there will be some LO phases here or not F.
At least in F.
I suspect so. Yeah.
I'm going to ask the same question I asked Eduardo on Monday. So it seems like your pairing interaction doesn't allow for triplet because you only have spin up, spin down. And my comment is that, spin triplet in this situation always has this BCS log, fully gaps the Fermi surface. And in all the calculations that we did, that just wins over these singlet phases.
Yeah. It depends on how close you are to the onset. As I showed, there is this very large maximum in the pair susceptibility, in the pair correlation function, that there is at finite momentum, there is a very large maximum. So even though one has an infinitesimal transition, the other one can compete effectively. And actually, Daniel Achterberg he showed some years ago in the context of FLO that the P-wave part actually can help the LO term essentially make it stronger. Is that correct, Daniel? He just sent me a paper he wrote 15 years ago.
Yeah, it's entirely right. I am limiting myself to spin singlet. I'm not considering spin triplet. Our initial motivation was, we were also thinking of this could probably happen in a proximity structure. I think the most superconductors we know are spin singlet, especially S-wave, but we know a bunch D-wave too. So yes, I have no idea what this would look like if you did it in spin triplet. Maybe it would be similar for actually a very similar motivation. Yeah, okay, good. Then I can continue. Yeah, so to just explain this Yoda ear diagram, so this along this axis is what people have done for a long time. So you take your spin DNR superconductor, you crank up a magnetic field, and you get the FF phase. So here having a FF phase is not surprising. You should have that. What I showed before was along this line, and that's saying I'm going to set at 0 external magnetic field, and I still get this FF phase, it's finite momentum phase. And you can it happens because the altermagnet nodes aligns with the superconducting nodes, and that's why we didn't get it in the S-wave phase. And really, when you align the nodes, you really take away the regions where the BCS state wants to live, which is a nodal region, and you really promote the spin-splitting feature of the Fermi surface. So that's why conceptually we won't get this from the S-wave, but we get it from the D-wave. So this might be something to think about if you extend this to a P-wave pairing. That you really probably have to think about how the node structure aligns. Then we also had, and this comes with this ear feature, there is a path here where you can sit, where you have a certain altermagnet, and if you're if a specific material, you can maybe sit out there and you crank up, which means that without magnetic field, you're not superconducting, and you crank up magnetic field and you actually enter a superconducting phase. So this is a field-induced region, and it could be, maybe you want to think, maybe this was just the model parameters, but it's actually reasonably easy to understand why it would happen when you start thinking about it, and I think it was a rather generic feature. So here I plot the Fermi surfaces as a function of magnetic field, and you see they distort, of course, with the magnetic field, and at some point you end up with a Fermi surface where you start overlapping up here, and this is where you now can do BCS pairing in this region. You couldn't do pairing at low magnetic field, but you can do it at high magnetic field. And we can also see that if you plot the pair density, sure enough, the pairs live in this region. And then if so that's why you go into the BCS regime, and then you crank up the magnetic field even more, and you go into an FF regime, and then you kill superconductivity. So based on this feature of having this ear is reasonably generic, and it comes from just the structure of the Fermi surface and how it distorts the magnetic field. So that was the first endeavor we did into altermagnets, and showing that we really could get finite momentum pairing, and especially when the nodes align, and we also had this field-induced superconducting state. And if you have this what are the parameters here? They seem rather high. This was all done in normalized units, and there was one parameter that was hidden here, and that was the strength on the superconducting state, and we had to have it rather high to be able to solve in, because it's rather large real space calculation. But if you take down this, the strength of the superconducting state, essentially V in your calculations, you still keep the ear structure. You change the shape a little bit, but it's still there. And then if you do some translate our coordinates, sorry, not coordinates, parameters, and you have T, say, around 100 millivolts, milli eV, then the magnetic field around 0.01 would be around 16 Tesla. So we think this, going into this field-induced superconducting state, should be possible to do in some reasonable altermagnet. Okay, so that was the first we did, and then de Malle made a really nice observation. He said, okay, but I have this FF phase, shouldn't I have a diode effect? So then we set out and look at the diode effect, and what I plotted here is the efficiency that we can find. So let me explain how we did this. Well, actually, we already heard about the diode effect, but let me just maybe repeat it. So here is where you have a dissipationless current in one direction only, and in the other direction you have a dissipative current. So you can think about it a little bit like this. You have a higher critical current in one direction and in the other. So when you order this regime where the current is high in one direction, not in the other, you have this regime of a diode effect. And it requires both broken time reversal and inversion symmetries. So this FF state is natural candidate, it modulates in space, and it has broken time reversal. And the efficiency would just be the differences in the critical current going in both directions. And at least when we did this work, we sort of found in the literature seemed to be around 60% was the highest efficiency that people had reported. There. So we set out to calculate this effect. So we kept the same spin singlet D-wave model they had before, and we solved again self-consistently for each Q, and the ground state is again a Q star. But then we also extracted the current. We calculated the current for each Q, and of course the current and the ground state needs to be 0, but then the current at finite Q that's not the ground state will just give you actually the current at that Q, and then from there we can extract the maximum current, and from the maximum current we can get the efficiency. And that is that's how we got this diagram, this phase diagram with the efficiency plotted. So I was thinking I would go through here because one can understand why you get the different colors here relatively easy by just looking at the energy and the currents in the system. So first we look in the deep FF phase. I'm going to look at these 2 points here, those are circled. So what I plot here in the upper part is the energy as a function of Q, and in the lower part is a current. And the current is calculated, it's just a bond current we calculated. And you see here, see where I'm there, this is the minima. So this is the minimum of the energy, so this is the ground state. And sure enough, the current is 0 in the ground state as it should be. And then we know in the superconductor, the current is going to be related to the derivative of the energy with respect to Q. And sure enough, you see that the current that we calculate is this current here is the derivative of this curve. Now, we didn't calculate as a derivative, so this was sort of an observation, sort of a sanity check that we did. And you see here that the current here is normalized, so it just reaches plus and minus 1 as most. So here you have a current that goes down to minus 1, and in the other direction is maximum around 0.4, so efficiency is minus 0.4. And in the other case, it's about the same. So that explains why we have a high diode effect in the FF region, but it's not perfect. But then we went to these other two, sort of the red regions in this phase diagram, so these 2 points, and then the energy landscape look a little differently, and that's why we get very high diode effect. So here, if we first look at down here at the triangle here, we have an energy landscape that looks like this. So here's the minima, but the BCS state is also a minima. In between there you have a little maxima, so that means the current is going to wiggle a little back and forth, but overall it's rather low current in that direction compared to the other direction. So I get a rather high efficiency, but it can't reach 1 because I need to go from minima to maxima in one direction. But in this point up here, I don't need to do that because this transition goes from having the FF state sit in a minima, but the BCS state is actually a maxima. So when I go very close to this FF to BCS transition, I end up actually flattening the whole energy landscape, which means I have no current. I cannot carry current in that direction, and therefore I reached a efficiency that's extremely high. So this particular point, it was 0.9, but the closer you get to the phase transition, the higher is the diode effect. Yeah, so you can get a large, but you can even get a maximum or a perfect diode effect, just simply because the FF state is a minimum and BCS is a maximum. So first we'll think, okay, so maybe this is just, we just happen to stumble on this and tune some parameters and will go away, but it shows actually more or less, well, it is protected by a topological phase transition in the band structure. So here I plotted in red all the points that has a high superconducting diode effect, and the blue line is the transition between a band structure that has the nodal points to one that doesn't have them, and that of course would always happen as a function of magnetic field when I apply that. And you see they are essentially perfectly correlated with each other. It means, which also is where this transition from the FF to the BCS state is happening. So you will always have these large efficiency regimes just because you have this transition of the band structure between the nodal and the nodeless as you tune the magnetic field in the structure.
I was just wondering, you plotted this as a function, I mean, normalized to IC+. So, I mean, there's a ratio, of course, that approaches 1, it seems. But what about the absolute current? Is it like really finite in one direction and non-zero in the other, or is it more like a 0 divided by 0 that
no, it will be finite in the other direction because you have. No, you're entirely right that you normalize to that. But the derivative in the other direction is finite. It's not. It doesn't go to 0.
Okay. Does it go down or?
No. So I don't remember exactly, but it's not. It doesn't approach 0. So you will have a finite value in that way.
I see. Because for us in most calculations, to get really high efficiencies above 80 or 90, you have to get kind of like close to, you know, like making the superconductor like almost unstable already sometimes, and then you can get really high. But okay.
Yeah, I think yes. I mean, so it's a good question, but I think since this is a finite Q from here to I reach the normal state, I will reach a finite current in that direction. So it's I don't know how big the stability region is, but it exists at least as far as we know. Yeah. Good. Okay, so that was a story about the superconducting diode effect. It will be large in all FF regions. That's been known before, but what we found here was this perfect diode effect, and it's protected by this topology in the band structure when you increase the magnetic field. Let me just spend the last few minutes showing what I think is one needs to be a little careful when looking at superconductivity in altermagnets. And this was something we didn't think about first when we started. We took this two-band model that everyone seemed to do, and we were happily using it. But then we started thinking a little bit, what are we actually doing, how we implemented superconductivity. So we went back to a little bit more complicated model. So say, well, okay, we have two sublattices and we have two spins. So if I'm doing this with this model, then I should have four orbitals, so 4 bands. So I have on the A side, I can have up and down, and on the B side, I can have up and down. And if you do that, you have some sort of spin-degenerate dispersion that is insensitive to both spin and sublattice. So this first point here, we have a crystal field splitting that is going to be insensitive to spin, but differentiate between sublattices, and then we have an exchange field that sits with both Pauli matrices in the Z direction. And then how do I go to this from the two-band model that I used before? Well, I can say that if J is big and TAM is a little smaller, then the bands separate, and I get effectively 2 bands like here, where I have B is down and A is up, whereas the 2 other ones are at higher energies. So if I want to write now a 2-band model based on this, I would just take, if I put my Fermi level here, I would just take the A upside and the B downside, and that is of course the Hamiltonian I used before. I have some spin degenerate band structure, and I have this TAM term here that differentiate. And then I have a sigma matrix here, but now sigma matrix is actually encoding spin and sublattice. Before I was just sort of thinking about the spin, but it really comes from encoding the spin and the sublattice in this model should be locked with each other. And if you start thinking about that, then I actually put some constraint on the pairing you can have in the system. So if you start with spin singlet pairing and you said, okay, I'm going to do S-wave pairing, the form factor is 1, and in real space it means I'm just sitting on site, so it's a completely homogeneous pairing in K-space and fully on site. That can actually not happen here because the A site has spin up and B has down. So if I want to do spin singlet pairs on the same site, there's no way to do that actually in this model if you think about where this orbitals is coming from. So you shouldn't have any conventional S-wave pairing, or I should say S-wave pairing with new modulation in K-space. If we look at the other simple spin singlet states you can have, well, we can have extended S-wave, it lives on nearest neighbor, and we can have 2 different D-wave solutions. And now some of these will be allowed because you can pair spin singlet on nearest neighbor sites because that has the correct spin structure. So the extended S-wave will be allowed, and the D-wave state that I had before is also allowed even in this picture. But the DXY, simply DXY here will not be allowed because it lives on next nearest neighbor, and then again that is A coupled to A or B to B. And if you do the same exercise for the simplest P waves, well, if you have equal spin triplet P wave, so you align the 2 spin and you want to do that on nearest neighbors, which gives you the smoothest oscillations in K-space. You can't do that because the spins on nearest neighbors want to be anti-aligned. They want to be a mixed spin triplet state. So the mixed spin triplet state is allowed on nearest neighbor, but the equal spin shouldn't be allowed. Now, this is based on the simplest form factors. One can go, of course, to higher order harmonics, and then you can get S-wave or P-wave and so on. But the simplest spin singlet S-wave or equal spin triplet P-wave shouldn't be allowed in the simplest models if you go to a 4-band model. So I think with that was actually everything I wanted to say. So I've been talking about finite momentum superconductivity and field-induced superconductivity that can easily happen in an altermagnet if you align the nodes between the altermagnet and the superconductor. I show that it has a large spin diode effect in the FF regions, and we can even get a perfect spin diode, so superconducting diode effect that's protected by topology at the BCS to the finite momentum pairing transition. And I'm trying to argue for why one shouldn't really consider conventional S-wave pairing or the simplest equal spin pairing superconducting in an altermagnet just because it has this sublattice structure that you need to take into account when you think about pairing. So with that, I thank you for your attention.
Thank you very much. I don't know how you did it, but you are in time. This is a very rare event. Are there further questions? We had already a few. Please.
So your diode effect must depend on the linear combinations that you get of the pair density waves. So the FF phase will have a different diode effect than the LO phase because, loosely speaking, the LO phase again restores inversion symmetry. Have you thought about this? And there's actually even other phases that you can get or beyond those. But
the short answer is no. We took the state we had and we calculated the diode effect. But it is, of course, an interesting question, especially if not the FF state is the lowest state. Yeah.
Is there further questions somewhere? So I'm a DFT person, like Ole Eriksson. And of course, we also want to do superconductivity, especially at interfaces, and you also would like to do proximity effect. So the way we do it is actually by combining Hohenberg and cone with Bogoliubov de Gennes. So when you do that, you have the Hohenberg cone for the electrons, you have the Hohenberg cone for the holes, and you have a pairing potential delta. So what I noticed is that your pairing potential has a Q dependence. we have forgotten this. So I was thinking what the message you have is that we should also introduce in the Bogle-Huber maybe a Q-dependent pairing and then minimize the energy as function of the Q. Is that the message I received?
Yes, if you want to think about superconductivity in an altermagnet, I think one should do that.
Yes.
Now, it gets a lot, even in this model calculation, it gets a lot more expensive because now I'm just not solving over one unit cell. I have to solve over the modulation of Q, and the smaller Q I want to have, the longer is my cell. So it gets a lot more expensive, which will happen in your DFT calculation too. So
This DFT calculation is already so expensive.
yeah, so maybe the answer is
because,
not so much.
With superconductivity, you're talking about milli EV and sometimes micro EV. So you have the K-point resolution like crazy. But I have a little bit of modulation, more or less. Probably expense square is also only just
I mean, it will scale your unit cell. You can do small modulations, of course, but the Q we find is generally vary all over the place. It's not sort of a simple Q. So in general, yes, but practically might be.
So I got this idea, but now I have to work 2 years on it. The orbital dependence we have. Yeah, the orbital dependence we have. Are there further questions? If not, I thank you very much.